So far we have examined how micro nanoplastics interact with and disrupt human cells. We now turn to how the impact of these same charged particles extend beyond the human body into the oceans, atmosphere, and climate systems. To explore this topic, I'm pleased to introduce Dr. Kára of the ALLATRA Global Research Center. He holds PhD in discrete mathematics and algorithms from Charles University in Prague, and his research focuses on natural disasters, geodynamic change, and the environmental impacts of micro and nanoplastics. Dr. Kára, the floor is yours.
Thank you. The impact of micro and nanoplastics on climate is an area of active research. One fact we already know, though, is that micro and nanoplastics do affect water cycle. So what does this influence involve? Water vapor in the air does not condensate into raindrops on its own. It needs particles to condensate around, so-called condensation nuclei. Naturally, these are particles of dust, sea salt, soot, or other aerosols. As Anna already told us, there is substantial amount of nanoplastics in the air, and the research published in journal Nature has shown that plastic particles in the air act as condensation nuclei for water vapor. When there are more condensation nuclei in the air, the same amount of water is distributed among more droplets. Thus, initially, these droplets are smaller, and it takes them longer time to grow to the size at which they start falling as a rain. But eventually, when the rain starts, it is more extreme, because more water has accumulated in the cloud overall. Thus, when the concentration of nanoplastics is high enough, they first contribute to prolonged periods of drought, followed by more intense rainfall and possibly causing flooding. Similarly to affecting rain, nanoplastics also affect how droplets freeze into ice. Normally, pure water droplets freeze at a temperature of around -38 degrees Celsius. In presence, the research from Pennsylvania University has shown that in presence of nanoplastic pollution, the droplets usually freeze already at temperatures of -18 to -24 degrees Celsius. Due to the fact that raindrops freeze at higher temperatures, hail is created at lower altitudes. This way, nanoplastic pollution contributes to more frequent creation of hail and creation of larger hailstones. On this slide, you can see graphs from European Severe Database showing how the frequency of large and very large hail is increasing in Europe over the last 20 years. Here you can see some samples of the hailstones. If we take long-term trends, then the chances of large hail in Europe are growing by about 20% per decade since the 90s. Similarly here, we can see how the chances of heavy rain are growing in Europe over the last 30 years. These events are causing significant damage, and nanoplastics are apparently contributing to the increase of these extremes. To summarize, micro and nanoplastics affect the condensation of water vapor and cloud formation, which leads to an increase in intensity of storms, thunderstorms, and other destructive natural phenomena. Since the effects of charged micro and nanoplastics isn't taken into account in our models, these particles are possibly also leading to higher inaccuracy of our weather forecasting and climate modeling. Now, let's move from the air into the ocean. The ocean and the atmosphere are a single climate system. Water has the unique capability to absorb enormous amount of heat. For comparison, just 10 meters thick layer of the ocean is able to absorb more heat than the whole atmosphere. Ocean absorbs heat during the day and releases it at night, thus smoothing out temperature fluctuations. Ocean thus plays a key role in maintaining planet's climate stability, acting as a kind of natural air conditioner. The ocean also removes heat from tectonic plates and releases it into the atmosphere. We hypothesize that large-scale pollution of the ocean with micro and nanoplastics is disrupting this precise cooling mechanism. Nanoplastic particles concentrate in the ocean in three main layers: at the bottom, at the surface, and in the middle in the area of thermocline, where the water temperature and thus density sharply changes. Plastic particles with surface charge interact with water molecules at the level of hydrogen bonds, and this alters the chemical and physical properties of the water, possibly slowing the heat dissipation into the atmosphere, and thus contributes to creation of zones of overheating inside the ocean. We hypothesize that the concentration of micro and nanoplastics in the ocean is sufficient to affect the heat exchange within the ocean. This, in turn, may lead to less heat being removed from the Earth's interior lithospheric plates, cooling less. As the graph shows, The temperature of our oceans is increasing at unprecedented rates. In fact, over the last few decades, the rate of warming ocean has accelerated by 450%. Now, the ocean isn't warming only at the surface, where the ocean is heating from the sun and the atmosphere. In fact, the surface heating affects only the upper 700 meters of the ocean due to mixing. But as you can see from the temperature profile data, since about 2017, the whole depth of the ocean up to almost 2,000 meters is abnormally warm. So what are the reasons of such intense warming of the ocean? According to our hypothesis explained above, the first reason is the concentration of micro and nanoplastics in the ocean. Since mid-20th century, the amount of plastic pollution entering the ocean is rising sharply. And all of this plastics is degrading into micro and nanoplastic particles. Now, over the same time period, we see a steady rise in the ocean surface temperatures. In Europe, we are particularly affected by this. Microplastic pollution in the Mediterranean Sea is one of the most severe in the world. It's 7 times the global average and 4 times higher than in the Northern Pacific, the area widely known for plastic pollution. Thus, it is quite possible that micro and nanoplastic pollution is already significantly contributing to the rise of heavy rain, large hail, tornadoes, and other extreme weather phenomena we observe in Europe. Now, temperatures and other extremes aren't growing only in Europe. As you can see in the graph, year 2025 has been the 3rd hottest on record, only marginally colder than the 2nd warmest year, 2023. Similarly, the amount of heat stored in the ocean, so-called ocean heat content, has grown by 23 zettajoules, which is, for comparison, about 37 years' worth of energy production of the whole humanity. Traditionally, this heating is attributed to the emissions of anthropogenic greenhouse gases. However, fast warming rate in recent years is significantly surpassing predictions of our climate models. Let me quote Dr. Gavin Schmidt, director of NASA Goddard Institute for Space Studies. The long-term trends we understand, and it's being driven by the greenhouse gases, it's being driven by anthropogenic effects. But what happened in 2023 was that, and then plus something. And that plus something is much larger than we expect or as yet can explain. This demonstrates how traditional climate scientists are confused by the recently observed fast warming of our planet. As you can see, the warming steadily continues in 2025 as well. On these graphs from a study published on January 9th in the Advances in Atmospheric Sciences showed that although in 2025 the surface of the ocean was not record warm in 2025, that's the graph on the right, the total heat that has accumulated over the year in the ocean was the highest since the measurements began. We are of the opinion that although anthropogenic greenhouse gases contribute to the long-term warming trend, they cannot explain currently observed fast heating, indicating there are other important factors that are impacting the climate and that are not taken into account. A factor we already spoke about is the pollution with micro and nanoplastics, which possibly impacts the ocean-atmosphere gas exchange, cloud formation, water cycle, as well as heat transfer within the ocean. However, we don't think this factor alone can explain the fast warming of the planet. Our hypothesis suggests that the geodynamic changes are another important factor contributing to the planet's warming. That is, activation of the Earth's interior increasing the geothermal heat flow, heating the oceans from below, and thus consequently the whole planet. Let me now pass the word to John, who will be speaking more about these changes. Thank you.